Welcome to the channel where we build real-world solutions. We explain complex concepts in simple language.
All right, welcome to this explainer. Today, we're going to absolutely demystify Docker for beginners and freshers. We'll be moving step by step from those universal, pull-your-hair-out developer headaches straight through to real-world applications. Honestly, whether you're just hacking away on a personal project or stepping into a massive tech organization, understanding Docker is a total superpower.
So, let's dive right in by starting with a question that has frustrated literally every software engineer in history. Have you ever spent hours perfectly crafting an application, right? It runs flawlessly. Then, you hand it over to a colleague and you immediately watch their terminal just explode with errors. It's completely baffling. I mean, you both have the exact same code, so what on earth went wrong?
Here is our roadmap for today. 1. The classic developer problem. 2. Enter Docker, the solution. 3. Images versus containers. 4. Docker versus virtual machines. And 5. Some practical Docker examples.
Okay, kicking things off with Section 1, the classic developer problem. Let's set the stage here with a very real, very painful scenario. Imagine you build a Node.js app on your local machine, using, say, Node 16 and MongoDB 4.2. Great. But when a teammate tries to replicate it on their shiny new Mac, they instinctively just download the latest versions, Node 20 and Mongo 6. Suddenly packages conflict, things break, and your perfectly good code leads to massive bugs. You've just earned the unofficial Works on My Machine certification.
Yeah, this version mismatch gives rise to the most classical problem in software development. But it works on my machine. It's a funny excuse, sure, but it forces large teams into a total error-prone nightmare. Manually setting up and maintaining exact environment dependencies across dozens of developers, it's just not sustainable. So how do we fix this messy manual installation process? How do we ensure everyone is running the exact same environment, no matter what operating system they happen to use?
Which brings us to Section 2. Enter Docker, the solution.
So here's the big reveal. Docker allows you to create a single bundle containing your app and absolutely everything it needs to run. By packaging the code, the runtime, the system tools, and the exact versions of all your libraries into one standardized unit called a container, you are completely standardizing the environment across the entire team.
By sharing this standardized unit, it literally doesn't matter if your teammate is on a Mac, a Windows PC, or Linux. The container ensures that exactly Node version 16 and Mongo version 4.2 are going to run flawlessly. And beyond just portability, it's exceptionally lightweight. You could actually run two completely separate applications on your single laptop, one needing Node 16, another needing Node 20, running simultaneously in their own isolated containers, without them ever interfering with each other. It's wild.
Moving right along to Section 3, Images versus Containers.
Now, people mix these terms up all the time, but they are very different things. If you think about object-oriented programming, an image is kind of like your static class, while a container is the actual running object that consumes your system resources. The class itself doesn't do the heavy lifting or eat up dynamic memory, right? It just defines what the object will be. Similarly, an image is just the instructions, while the container is the living, breathing environment actually doing the work.
You see, you never actually share a running container with your team. That'd be like trying to share a running car engine through the mail. Instead, you share this lightweight, executable blueprint, the Docker image. Your teammate receives that blueprint, and their local Docker engine uses it to build an exact replica container right there on their machine.
So how does this actually play out? Well, when you type a command, Docker checks to see if you have the required image locally. If you don't, it quickly fetches it from a public registry called Docker Hub. Then, it instantly spins up a running container from those layered instructions. And I mean instantly. It happens in seconds.
All right, Section 4, Docker versus virtual machines.
Now you might be sitting there wondering, wait a minute, haven't virtualization and virtual machines existed for years? Why is Docker suddenly taking over the entire software world? Well, the answer really just comes down to size and speed. Unlike heavy virtual machines that virtualize the entire underlying operating system kernel, Docker only virtualizes the application layer. VMs take up gigabytes of space because they have to carry a whole guest operating system with them. Docker containers, they're often just megabytes, and they boot up instantly because they skip starting an entire OS from scratch.
Because Docker has so much less overhead, creating, updating, and deleting these containers is blazing fast. They just share the kernel of your host machine. Now, actually, it is worth noting that VMs definitely still hold an advantage for absolute cross-kernel compatibility. Like if you need a strict Windows kernel environment on a Mac. But for modern app development, Docker's speed and size make it the absolute winner, hands down.
Okay, let's get to the really fun stuff. Section 5, Practical Docker Examples.
Enough theory, let's actually bring this to life and see what it looks like on the command line. With just one simple command, docker run-it Ubuntu, using that interactive tag, you can jump straight into the root directory of an isolated Ubuntu environment, right there on your host machine. You haven't actually installed Ubuntu on your computer, but suddenly you're inside a terminal that totally thinks it's a dedicated Ubuntu machine. You can make changes, install packages, and then simply delete the container without it ever affecting your actual computer. Now, because containers have their own completely isolated file systems and network ports, we do hit a tiny hurdle. How do we actually talk to an app running inside a container from our regular web browser? Well, we use something called port binding. This basically just routes traffic from our local computer directly into the running container. So, for example, you might route your local port 8080 straight to the container's internal port 3306.
Of course, when we're building real apps, we usually don't just have one container, right? We might have a backend server over here in one container and a database in another. We need these multiple containers to communicate securely. This is exactly where Docker networks come in. Think of it as creating a private chat room for your containers. And to manage the whole shebang, we use Docker Compose, which replaces those complex, mile-long terminal commands with a clean, beautifully structured YAML configuration file.
Bringing it all together for a final project scenario, let's say we have a Node.js application. Instead of going through the hassle of installing MongoDB directly on our computer, we just define our MongoDB image, our Mongo Express user interface, and our environment variables, like database passwords, in a single dockercompose.yaml file. Then we launch it all in the background with one extremely elegant command, docker compose up-d.
And here is the true magic of Docker. Your local Node application is seamlessly fetching and posting user data to a MongoDB database that exists entirely inside an isolated container network. You can even visually inspect the data using the Mongo Express container running right alongside it. And honestly, the best part? When you're done coding for the day, you simply shut the containers down, your computer remains perfectly clean without any residual database software clogging up your system. Docker completely eliminates the friction of setup and dependencies. You never again have to worry about whether something is going to work on a colleague's machine or if a messy database install is going to corrupt your local environment. You now have a standardized, lightweight, and incredibly powerful tool right at your fingertips. So the only real question left to answer is, what amazing software are you going to create next?
Hey everyone, welcome. Today, we are turning you into absolute masters of container image management. Look, if you've ever felt a little overwhelmed by exactly where your application goes after you build it, you are entirely in the right place. In this explainer, we're going to completely break down Docker Hub. It's basically the central nervous system for Docker users. We'll be covering the whole shebang, from core concepts to the exact workflows, security protocols, and those tricky operational limits you need to know so you can manage your images just like a senior engineer. Let's get into it. To kick things off, let's start with a really foundational question. Where exactly does your code go after it gets compiled? Well, think of software development kind of like baking. Writing your source code is a lot like gathering all your raw ingredients, right? You've got your flour, sugar, eggs, but you can't just hand someone a bag of flour and tell them to enjoy a cake. No way. You have to actually bake it. In the software world, compiling your code and all its dependencies into a container, that's your baking process. And once you've got that perfectly baked, ready-to-eat cake, you need a display case to show it off and actually deliver it to your customers. Okay, let's dive into our roadmap for today. First, code versus container repositories. Second, setting up your repositories. Third, the push and pull workflow. Fourth, Docker Hub security best practices. And fifth, managing your rate limits. Section 1, Code versus Container Repositories. Now, this is a really classic point of confusion for newer developers who are transitioning into DevOps, specifically figuring out the difference between the two most popular hubs out there on the internet. So before we compare them, we need to nail down what an image repository actually is. Simply put, an image repository is a centralized, cloud-based storage space. But listen, it does not hold lines of code. Instead, it holds your compiled code plus absolutely all of its dependencies, neatly packaged together as a ready-to-run software image. So when a testing team or a server pulls this image, they don't have to scramble for extra software. Every single thing they need is already tacked right inside.
And this analogy brilliantly illustrates the difference between our two big hubs. GitHub, that's your code repository. It handles version control for your raw source code, whether that's C++, Java, Python, JavaScript, whatever. It's the pantry for your raw ingredients. Docker Hub, on the other hand, is your software or image repository. It's the destination where your CI/CD pipeline pushes the final, compiled container. It's literally the display case for that baked cake we talked about. So you store your code in GitHub, but you store your deployable containers in Docker Hub. Makes sense, right?
Section 2. Setting up your repos.
So once you actually sign in and hit that Create Repository button, your absolute most critical choice is your visibility. Much like GitHub, Docker Hub gives you two main flavors, public and private. If you go with public, your image is going to show up in Docker Hub search results. That means anyone on the internet can see it, pull it, and use it, which is fantastic for open source projects. But if you're working on proprietary company software, you are definitely going to select private. With a private repository, only you and the specific team members you explicitly authorize can view, pull, or push to it.
But hey, there is a pretty critical limitation you need to be aware of right off the bat. If you're just starting out on a standard free account, you get exactly one private repository. Just one. However, you can create as many public repositories as you want, unlimited. So if your organization needs multiple private repos to secure a bunch of different microservices, you're definitely going to need to look into Docker Hub's upgraded paid plans.
Section 3, the push and pull workflow.
Okay, so we know how to configure a repository, but how do we actually get our images in and out of it? I want you to think about this for a second. What actually happens under the hood when you open up your terminal and type docker pull Ubuntu? It honestly seems like a simple download command, right? But there is actually an incredibly efficient mechanism working quietly in the background. So the really cool part here is that Docker doesn't just blindly download files from the internet every single time. Step 1, the Docker daemon actually checks your local machine's cache first. If it finds the image layers already sitting there, it uses them instantly. Step 2, if it doesn't find the image locally, well, only then does it reach out and connect to the Docker Hub central registry. And step 3, it downloads those missing image layers. Once they're downloaded, it caches them locally for next time. It's a brilliant system because it completely saves time and bandwidth, which makes your future container builds lightning fast. Now, what if you're on the other side of things? You've built a custom image locally and you want to upload it. Well, here is the exact sequential workflow you need. First, you've got to authenticate your terminal by typing docker login and tossing in your Docker Hub credentials. Second, you have to use the docker tag command, and you must format this tag perfectly. It's your Docker Hub username, a slash, the repository name, a colon, and then the version tag, something like latest. Finally, once it's tagged correctly, you type docker push, followed by that exact tag name. Docker will then take over and upload all the layers of your custom image straight into your shiny new cloud repository. Section 4, Docker Hub Security Best Practices. Because Docker Hub makes it so incredibly easy to share software globally, it's also, unfortunately, a massive vector for vulnerabilities. You know what they say, with great power comes great responsibility. So here are your absolute non-negotiable security essentials. First up, use multi-stage builds in your Docker files. By only copying your compiled binaries into the final image and leaving all those bulky build tools behind, you drastically minimize the image size. And smaller base images don't just mean faster downloads. Critically, they mean a much smaller attack surface. Second, you have got to scan your images for vulnerabilities during development before you push them. And you need to keep scanning them in production to catch any newly discovered zero-day threats. Third, when you're pulling base images, always look for the official image or verified publisher checkmarks. That's how you ensure you're getting trusted software straight from the actual vendors. But what if you absolutely need to use a community-created image? The golden rule here is trust, but verify. Let's say you're searching for a MySQL image. Please don't just grab the first one you see. Look for the official image that boasts over 1 billion downloads and 10,000 plus star ratings. And even more importantly, Docker Hub actually provides security insights right there on the UI. Check those vulnerability reports. If an image is sitting there showing 41 critical and 37 high vulnerabilities, you should probably walk away and look for a safer alternative or a newer tag. Whatever you do, don't just casually pull compromised software into your local environment.
Section 5. Managing your rate limits. Okay, let's talk about a massive operational headache that constantly catches automated pipelines totally off guard. 429. If you ever look at your terminal logs and see the HTTP status code 429, it means one thing: you've hit the dreaded Docker Hub rate limit. Docker strictly enforces a fair use policy. Basically, if your account is pulling an unusually massive amount of data, they are going to throttle or restrict your activity just to protect the platform's performance for everyone else.
Check out how these limits actually break down based on your account status. It's pretty interesting. If you're an anonymous user, meaning you're just pulling images without actually logging in, you're capped at just 100 pulls per IP address every 6 hours. But here's the trick. Simply running Docker login with a completely free authenticated account instantly doubles that limit to 200 pulls every 6 hours, literally double the bandwidth for free. Now, if you're operating in a heavy enterprise environment, paid subscribers can customize this to allow up to 5,000 polls per day. Knowing exactly where you fall in these tiers is vital to keeping your deployment pipelines from randomly failing on you.
So, the big question: how do we actively stay under that limit and dodge that nasty 429 error? I've got 3 actionable tips for you. First, heavily utilize local caching so you aren't just needlessly pulling the exact same base images repeatedly over the network. Second, configure your CI/CD automation pipelines so they pull images only when absolutely necessary, rather than triggering a massive pull on every single minor code commit. And finally, get into the habit of performing regular cleanups. Nuke those outdated or unused images to free up space. It makes your overall account usage way easier to manage.
Now, if you are just constantly bumping up against those rate limits, or maybe you simply want your container registry to live a bit closer to your actual cloud infrastructure, remember, you aren't locked in. While Docker Hub is definitely the industry standard, there are some incredibly robust alternatives out there. You could use the GitHub Container Registry, Amazon Elastic Container Registry, Google Artifact Registry, or you could even host the whole thing yourself using something like JFrog Artifactory. And the best part? The core concepts we covered today, tagging, pushing, and pulling, they remain exactly the same across all of them.
And that brings us to the end of our journey for today. You now know exactly how to differentiate your code from your containers, how to set up secure repositories, how to flawlessly execute the push and pull workflow, and how to navigate those pesky rate limits. But I want to leave you with a bit of a provocative thought to chew on. Your code is now containerized. It's highly secure. It's resting safely in Docker Hub. But is your production environment actually ready to pull and scale it effectively across a massive cluster? That, my friends, is the complex world of container orchestration, and it is exactly where you should focus your learning next. Thank you so much for joining me for this explainer. Keep building, keep securing those images, and I'll catch you next time.